Please, has he started? Because I can't hear any sound.
No, please. No, please.
No, madam.
Okay, thank you.
All right, good morning once again.
Good morning, sir.
Good morning, sir.
Good morning, Doc. From cold schedule, it seems this probably might be our last meeting, unless otherwise the class decided to do a makeup lecture. Then I'll be ready for that. Nevertheless, we should be able to finish all the topics today. If you're unable to finish, then we have to schedule another time. So, physical properties of alkynes, and this one, the trend is similar to what you know of the physical properties of alkanes and alkenes. So the lower members are gases, and because alkynes, like the other hydrocarbons, are non-polar, then it means that they'll be insoluble in what? Water. They are rather going to be soluble in non-polar solvents like benzene, carbon tet, petroleum ether, and the others. In terms of density, like we saw in alkanes and alkenes, the alkynes too are less dense than water, meaning when you add a small amount of alkyne in water in a test tube, you expect the alkyne to float on top, whilst the water stays down. The boiling point trend and the melting point trend also follow the same trend. That is to say, if you are increasing the carbon chain, the number of carbons in an alkyne molecule for open chain alkynes, there is a corresponding increase in boiling and melting point. So if you are dealing with an alkyne of 5 carbons and then an alkyne of 8 carbons, which are both straight chains, then you expect that the alkyne of 8 carbons will have a higher melting or boiling point than that of the 5 carbon. But then, when we start introducing side chains or branches, as we saw in alkenes and alkenes, branching has an effect on both the melting point and boiling point. Whilst branching helps to increase the melting point, it decreases the boiling point. So the degree of branching has a negative effect on the boiling point of the alkyne molecule. So when there are more branches, then you expect the alkyne to have a less boiling point compared to a similar alkyne, which is what? A straight chain. But then, oppositely, in terms of melting point, when there's more branching, then the melting point increases. So they are nearly the same as what we saw in alkenes and alkenes. So that is the physical properties of alkynes. Now, briefly, before we go to the synthesis, alkynes also undergo isomerism, structural isomerism. Alkynes also undergo structural isomerism, and
Sir, please, are you sharing your screen? Because I can't see anything from my side. That's the reason I'm asking, please.
please, can you see now, Festus?
The screen is visible now. We can see.
Okay, now you can see.
Internet.
All right. So I was saying that in terms of isomerism, alkynes also undergo structural isomerism, but they do not undergo geometric isomerism, the cis and trans. In fact, the cis and trans isomerism is only limited to what? The alkenes. Nevertheless, all the hydrocarbons undergo structural isomerism. In case of the alkyne, it is just changing the position of the triple bond that will begin to give you different isomers. And then also shortening the carbon chain and introducing branching. So take note of that. Now, synthesis of alkynes. How do you prepare alkynes? As far as this course is concerned, we are introducing you to at least 3 methods that we can use to prepare alkynes. The first and then the most predominant one is the dehydrohalogenation of vicinal dihalides. Dehydrohalogenation of vicinal dihalides. And on your screen, you see an example of a vicinal dihalide, which is having 2 halogens, let's say bromine and bromine, on adjacent carbons, okay, next to each other. That's what we mean by vicinal arrangement. If in between these 2 bromines there comes in a carbon, then that arrangement is no more vicinal. That arrangement is no more vicinal, and such a dibromide cannot be used to prepare alkynes. It is only the vicinal ones that can be used as starting materials. Now, the reagents and condition here is a strong base. You need a strong base to convert this vicinal dihalide into an alkyne. And the reaction is a double beta elimination process. The reaction is a double beta elimination process. Now the elimination is done by two consecutive dehydrohalogenation. And you know from your previous knowledge, when you say D, you are removing something. What are you removing? You are removing a hydrogen and then a halogen. That's how come we have the name dehydrohalogenation. So in the starting material there, you are taking one halogen and one hydrogen. Okay. When you finish, then you come and take another hydrogen and another halogen. That's why we say that it is done by what? Two consecutive dehydrohalogenation. So the removal of hydrogen and halogen is done 2 times before you can get your triple bond forming. And it is done using a strong base. It is done using a strong base. So why do we say it's a double beta elimination process? What it means is that you see the carbon that the two bromides are situated on, there are also two hydrogens there. So if let's say I am removing this hydrogen here, I hope you can see my cursor.
Yes, sir.
Good.
Yes.
If I'm removing this hydrogen here, what it means is that it is going to be removed not with the same bromine on it is on the carbon with, but then the hydrogen here will go with what? An adjacent halogen. That's the bromine here. So if you consider this carbon as alpha, then this one is what? A beta. So a hydrogen on the alpha carbon goes away with what? A halogen on the beta carbon. Then the second hydrogen here will also be removed with what? The other halogen on the other carbon. That's why we say it's a beta elimination process. Now the question is, why are these hydrogens being removed? These hydrogens here are acidic, or they've been made acidic because of the halogens. We know the halogens are highly electronegative, so they draw electrons to themselves. They push electrons to themselves. So because these two bromine atoms are drawing electrons to themselves, they end up pushing the electrons between the carbon-hydrogen bond to themselves, thereby making it weak. So the carbon-hydrogen bonds here become very weak, and when they are very weak, it means that these hydrogens can easily break off, or they can easily ionize in solution, and so that makes them what? Acidic hydrogens. And because they are acidic hydrogens, it means that a base can easily attack them in the normal acid-base reaction. So when the base come and pick on this hydrogen, its bond here will break here and form a double bond. When it form a double bond, then one of the bromines, the adjacent one, will break off. Then the base will come and pick on this hydrogen. Then its bond also will break onto this one. Already there's a double bond there, so it will break and form the triple bond. So now to form the triple bond, then the other bromine also will break away, and then you form your triple bond. So over here is a typical example of an alkyne, and then this is a base. It could be sodium in liquid ammonia. I'm giving you the type of base that can be used: sodium in liquid ammonia, sodium hexide, or alcoholic potassium hydroxide. You know, potassium hydroxide is a base, it's a strong base. So when you say alcoholic potassium hydroxide, that means the base is being administered in an alcoholic medium. Okay, and these are very strong bases, so they can be used to execute this kind of reaction. So for all that I've explained, this is the mechanism. Okay, this particular slide that you see here, for all that I have explained to you, that is a mechanism. So you could see that the NH2 minus, that is the base, picks on one of the hydrogens, and then its bond break here, forming a double bond. Then the adjacent bromine breaks off. So you get first a double bond forming, then the second hydrogen also gets picked on by the same base. Its bond breaks onto the double bond to make it a triple bond. Then the second adjacent bromine also breaks away. And finally, you form your triple bond. That is the alkyne. So this is the mechanism. And I keep on telling you that this course is an introduction course. It's just a preliminary organic course. So at this level, I am bringing the mechanism for you to appreciate what is happening, the detailed reaction, step-by-step reaction. But I will not tell you to show this mechanism in an exams, okay? Yours is to know that when I have a Visna dihalide, when I have a Visna dibromide, and I have a strong base, then my product will be what? An alkyne. And you should be able to give the structure of the alkyne that will be formed. So the second one is that maybe we might not give you the Visna dibromide to start with. Maybe we can give you an alkene, and you know alkene. One of the reactions of alkene is what? Its ability to react with what? Bromine in carbon test. It's one of the test reagents for unsaturation. So when you have an alkene and then it reacts with bromine in carbon test, we all know that if you are to be doing this reaction in the lab, what you see is the decolorization of the brown color of bromine. That tells you that there's a reaction taking place. So bromine itself has a brown color, and it can easily react with alkene because alkenes are very reactive. So when the bromine is reacting with the double bond breaks down to a single bond, and you have bromine being attached to each of the carbons which bear the double bond. And then you form this dibromo compound, which is a Visna dibromide. So it means if you have an alkene, you can react it with what? Bromine carbon text and create the starting material for preparing alkynes, which is a Visna dibromide. Then you can add your strong base, and then you form your alkyne. So that is another pathway that you can use to prepare alkynes. So all that you see here are more examples of the same method, okay? You can use alcoholic KOH, which is a strong base, and then it will pick on the acidic hydrogen. The bond will break, form a double bond first. Then the second hydrogen will be picked on. The H bond will break and form a triple bond. And then you have your alkyne synthesized. And when you are able to prepare an alkyne, there are enormous uses of alkyne. And you can go and sell it and make money, and maybe use some to pay for your fees before the end of semester exam begins, so that code do not sack you. Any question at this point?
Yes, sir. Please, sir, please pardon me. What is the R there? The R there stands for?
Okay, so
The previous one.
apart from the two halogens, okay, and then the hydrogens, which is our focus, the out there can represent anything at all. So you see, I'm giving you a general example. That's why I have represented those groups with what? R. So out there can be a methyl group, it can be an ethyl group, it can be an aromatic group, it can be any other group, it can be a long chain hydrocarbon, okay? But then our focus is on the two carbons, which is having the halogens and then the hydrogens. That is to be removed. Francis, are you okay?
Yes, sir.
Okay, Tahiru, no hand is up.
Yes, Doc. Please, Doc, I beg you. My phone went, or the network is not good. I'm at Bolga. I was just following you, and you were talking about the how to make alkynes, and you mentioned the halogens. That's where you remove hydrogens and halogens. From there, I didn't hear anything.
All right, so the lecture is being recorded, so don't worry. Just follow and then get the recorded version, okay? And then you get everything. All right. Any other? Peter, your hand is up before I continue.
Okay, Doc, thank you so much. From the start, concerning about the physical properties of alkynes, you made mention that when in terms of their structure, when we have a branch structure, So it strengthens the melting point than those in the straight chain. So, and I want to ask, if we have a straight chain of alkyne, and let me say octane,
Please
and we have
raise your voice
the
more.
one which is having a short chain, but okay, what I'm saying is that I don't know whether you are getting me.
Bro, raise your voice.
Hello?
Raise your voice so that we
We can hear you, but your voice is very down.
Hello?
Raise your voice, bro.
Because you are asking a very important question. So please raise your voice so that your colleagues can hear you. Oh, have you lost him? Yeah,
Hello?
Azuma, go ahead.
Please tell me right now.
Yeah, go ahead.
Doc, what I was saying
You
is
go
that
ahead. I'll manage.
considering okay. Then considering the long chain and the branch chain, you indicated that when we have a branch chain, that one is having its melting point is stronger than those in the straight chain. And what I want to ask here is that if I have a strong chain of alkyne, and for example, let me say octane, and I have another one which is having a branch chain, but that one is not long. Let me say butane, and it's having a branch chain. So considering that straight chain, which is having many carbons, than the one which is having branch but limited carbons, which one will have a greater impact in terms of melting point?
Great. So I've gotten your question very well, but then the examples you gave doesn't really add up, because if you say butane, which has a branch, butane, unless you tell us, the branch, the actual name, because butane can have one branch, one carbon, it can have two branches, okay, so that you have something like 2,2-dimethyl butane. You can have 2-methyl butane. So I would have wished that there's a specific, but then what is important is that all these things are determined experimentally, okay? And so for some of them, if the argument is very close, okay, unless you do the experiment, you determine it experimentally in the lab before you know which one have the highest melting or boiling point. So for examination, we will give you 2 or more compounds whereby it will be easier for you to compare. One, if I give you, let's say, octane, as you said, okay, and then I give you 2,2-dimethyl pentane, okay, 2,2-dimethyl pentane. Now the 2,2-dimethyl pentane will have 7 carbons because the 2 branches also contain carbons. Then the octane has 8 carbons. So you could see that there's only 1 carbon difference between them.
Okay.
In this case, the extra 1 carbon which the octane is having wouldn't have a significant advantage in terms of the molecular weight. So it is the branching which is in the 2,2-dimethyl pentane which will override in terms of the melting point. So in terms of melting point, the 2,2-dimethyl pentane will have what? The highest melting point because of the highly branched nature. But in terms of boiling point, the octane, which is a straight chain, will have the highest boiling point. I don't know whether I'll be able to help you out.
Yes, sir. I get it. Thank
Great.
you.
Thank you for your question. It's a very important question because exactly how you get examined in an exams, okay? So it's a very important question he asked. All right. So the others that you see are all examples of the first method, the dehydrohalogenation. Just that on the screen, what you see there is not a vicinal dihalide, but this one is what you call a germinal dihalide. Now, the difference here is that whilst the vicinal dihalide, the two bromines or the two halogens were on adjacent carbons, in the case of the germinal dihalides, the two halogens are on the same carbon at the end of the chain. So this time around, the two halogens that you are removing are on the same carbon, and then the two hydrogens you are removing are also on the same carbon adjacent to it. And that's what we call the germinal. But then in terms of the product, in terms of the condition, and then the mechanism, it is the same thing as we saw in the vicinal dihalide. So you can see that over here, the base, you see the two hydrogens that are to be removed, they are on the same carbon. Then the two bromines who are on the same carbon. Okay, so this is the germinal dihalide arrangement. In the case of the vicinal, the two bromines were on the adjacent carbons, and then the two hydrogens were also on adjacent carbons. But then the mechanism, you pick on one hydrogen, the bond breaks, you form a double bond. Then the base will come and pick on the second hydrogen, the bond will break onto the double bond to form the triple bond, and then the two bromines get removed. The same way as we saw in the vicinal dihalide mechanism. The other method for preparing alkynes, which is via Grignard reagent. This method, basically, you are preparing alkyne from another alkyne. Okay, unlike the first method, second method, where we need a vicinal or germinal dihalide, a strong base to prepare our alkyne, or we need an alkene, and then we first of all convert the alkene to the vicinal dihalide. For this particular method, if you are preparing the alkyne, you need an alkyne as a starting material, and then you prepare another alkyne from it. So higher homologous of acetylene or terminal alkynes are best used in preparing elongated or huge alkynes. Remember, at the alkyne introduction, I told you that we have two types. We have the internal alkynes and then the terminal alkynes. The terminal alkynes have the triple bond at the terminal end, and they have what? A terminal hydrogen. And so the terminal alkynes, I told you, are acidic. They are acidic because of the terminal hydrogen they have. But then the internal alkynes, the triple bond is in the middle, and they don't have the terminal hydrogen, so they are not acidic. So for this particular synthesis, you can only use a terminal alkyne to prepare another alkyne. You cannot use an internal alkyne. So what is happening is that the terminal hydrogens, which are acidic, get reacted with a Grignard reagent, and then you form this intermediate. Then depending on the kind of alkyne you want to form, that is depending on the chain, the elongation of the chain. Maybe you want to add 1 carbon, you want to add 2 carbon, you want to add 3 carbon. Then you choose your alkyl halide. So you see, I have represented the R here. That's the alkyl halide by R, because R here could be 1 carbon, that's a CH3. It could be a 2 carbon chain, it could be a 4 carbon chain, it could be a 8 carbon chain. So I have represented the chain by R, meaning depending on the kind of carbons you want to introduce or add to your terminal alkyne to elongate it, to extend it, then you choose a particular alkyl halide, and then you elongate it. I have already talked about the acidity of terminal alkynes, because the terminal alkynes have the terminal hydrogens, and so these terminal hydrogens can easily be what? Ionized in solution, and when they do, then they become what? Acidic. So I think this is already taken care of. All right. So when you have a terminal alkyne again, which we know are acidic, then what we are saying is that in the presence of a base, you can then pick on the acidic hydrogen and form the intermediate salt of it. And then when you do, then please, there's a feedback I'm getting. Someone is talking. Then you can add the appropriate alkyl halide and then extend your chain. Please, I have given you tutorials on all this. So some way, somehow, when I'm teaching or when you are revising or when you go back and you are watching the recorded video, make sure you link it to the tutorial questions given to you, and then that should help you to be able to solve almost all the tutorial questions on your own. Now, reactions of alkynes. We've gotten to know how to prepare alkynes. How do alkynes react? We got to know that alkanes are non-reactive because the carbon to carbon and the carbon to hydrogen bonds in alkanes are non-polar. The bond is not polarized, so they are non-reactive. But when we got to alkenes, we said alkenes are what? Very reactive because of the presence of what? The pi bond in the double bond. That makes alkenes very reactive. And of course, if you see alkynes, carbon, triple bond carbon, we have two of the pi bonds in there. And so those pi bonds contain pi electrons. And these pi electrons are readily available. And so that makes alkynes nucleophilic. That makes alkynes electron rich. So it means alkynes are also what? Reactive. Alkynes are reactive because the presence of the two pi bonds makes them what? Nucleophilic in nature. Okay. And the pi bonds contain the pi electrons. So there's a high electron density. And you know, electrons makes the system what? Reactive because they are negatively charged species. So that explains why alkynes are reactive. But the question I want to ask is, alkenes and alkynes, which one is more reactive and why? Alkenes and alkynes, which one is more reactive and why? Yes, Joshua.
Hello, good morning, Doc.
Morning.
Please, I wanted to ask a question before your question came in.
Okay, ask yours and then.
Okay, please. With the sigma bond and then the pi bond, why are the pi bond weaker than the sigma bonds?
Okay, so if you do hybridization, okay, during hybridization, you know, bonds are formed as a result of what? Mixing of what? Atomic orbitals, okay? So when you are mixing these atomic orbitals, then you form these bonds. Now, in forming the sigma bond, the mixing of the atomic orbitals is done by head-on overlap. So the head-on overlap is very effective and makes it the bond very, very strong. But then the pi bonds, doing the mixing of the atomic orbitals, they are formed as a result of.
Doctor.
They are formed.
Please, what is his question?
Do I continue?
Yeah, please continue.
I want to know his question, please.
Yes, sir. Continue.
So with regards to the pi bonds, okay, in terms of the mixing of the atomic orbitals, that leads to the formation of the pi bonds. The overlap is done laterally, okay, side by side. And side by side or lateral overlap it's not as strong and effective like the head-on overlap. So it means that any bond that is formed by the mixing of the orbitals from the side to side, okay, or the lateral overlap, those bonds end up to be very weak because the mixing or the overlap itself is very weak. So that leads to the reason why the pi bonds are weaker than the sigma bonds. And you know, because the bond itself is weak, what it means is that the electrons in there are not so much rigid. They are not restricted. They are not tight. They are readily available to even react easily. So if you ask your question, Joshua, that is the answer. Please, let's pay attention when your colleagues are talking, when they are asking questions. His question was that he wanted to know why sigma bonds are stronger than pi bonds. And it's not part of this course though, but it is expected that you have that basic idea or knowledge on hybridization. So that's what I was trying to take you back a bit and then explain. Please, any other question? Yes, Frank. Frank, go ahead.
So please, I do have a question. I mistakenly raised up my hand.
All right. So I think this is the reason why alkanes are also reactive. But my question is, between alkane, we know alkanes are non-reactive because the carbon hydrogen bond is what? Non-polarized. So the only way an alkane can react is under sunlight or heat. And we went through the photochlorination reaction. Without that condition, alkanes will not react. But we know that as for alkenes and alkynes, they react. And the alkenes, I made you aware that they undergo what we call electrophilic addition reactions because the alkenes are nucleophilic, electron rich. So when they see an electron deficient species, that's an electrophile, which is a positivity center, they react. And we saw the various reactions. The reactions that alkenes undergo, they are the same reactions alkynes also undergo. So under the reactions of alkynes, I will not even waste time because it's just a repetition of the reactions we saw in alkenes that we are going to see here. Just that whilst in the alkenes is a double bond, here it is a triple bond. But my question is, between an alkene and an alkyne, which one is more reactive and why? I will ask you this question in an exams, end of semester. Yes, Kekile.
Good morning, sir.
Morning.
Please, the alkanes are more reactive than alkanes because
come again.
The alkanes are more reactive than the alkanes. That's because
I'm hearing the same thing. I'm hearing alkenes and alkenes.
It's alkyne and then alkanes.
Alkynes and alkenes.
Okay, alkynes and then alkane. So the alkanes are more reactive than the alkanes.
Okay, so what you mean is that the alkenes are more reactive than the alkynes.
Yes, that's
very
because
the reason.
That's because the pi bond in the carbon-carbon double bond is weaker and more accessible to electrophiles. Whereas in the alkynes, only the strong carbon-carbon bonds, single bonds, are less reactive and require more energy to undergo reactions. Thank you.
Yeah, you are right. You are right. Maybe to add, why are the pi bonds in alkenes, why are they weak and readily available or accessible compared to that of the alkynes? Because they are all pi bonds. So how come that the pi bond in alkenes is readily available compared to that in alkynes. Okay, why? And even in the case of the alkynes, there are two of the pi bonds. So wouldn't that one have been more reactive than the alkenes?
Hello, sir.
Yes, go ahead.
Please, can you what I know that can we look concerning the pi bond? Both of them have pi bond, right? And she was saying the alkenes pi bond is weak, something like that, and more accessible.
Yes.
So concerning the pi bond, maybe I can use the hybridization of it, because the alkenes pi bond they undergo sp2 hybridization, but for the alkynes they have sp hybridization. So that make the alkynes, that sp hybridization less reactive, and the alkenes sp2 hybridization more reactive. I mean, that's what I know.
Yeah, what you know, you are only giving us information about the type of hybridization in the carbons atoms in the alkenes and alkynes. But then as to why the electrons in alkenes are readily available or easily accessible compared to that of the alkynes, you'll still not be able to touch on it.
When you look at the hybridization of the alkenes, you have let me say the S character is very small. I don't know.
The S character is very small.
Yeah, very less. That's make them more accessible. But for the alkynes, no.
Okay, Nana. So let me help you here. Again, your argument is talking about the bond strength. Okay.
Okay.
There's a difference between the bond strength and then the reactivity. The bond strength, the carbon-carbon triple bond is stronger than the carbon-carbon double bond. Because in the bond strength, we use what we call the S character. When you have more S orbital in your bond formation, then you are going to be stronger, because the bond strength is dependent on the S character. Okay. Now in alkynes, the hybridization is what? SP. Meaning you have what? 50% of the S character and 50% of the P character.
Yeah.
That makes them having more S character than the alkenes, which is SP2. Okay. So that argument is for bond strength. But then again, the point is that in the case of the carbon-carbon triple bond, okay, the electrons in there, the pi electrons in there, which we are saying they are not readily or they are not easily accessible like compared to that of the alkene, is because those electrons are much, much closer to the carbon kernel, the nucleus of the carbon in the case of the alkynes. Okay, and so, you know, the nucleus of an atom contains the protons, which are positively charged. So if these electrons are closer to the nucleus, what it means is that the attraction between the electrons and then the protons in the nucleus will not make those electrons, you know, easily available or accessible. And that is something different when it comes to alkenes. So if alkenes are more reactive than alkynes, it's as a result of the reasons our sister gave, Tekele gave, but then I'm also giving more information why those electrons are as easily accessible in alkenes as compared to alkynes.
That's the concerning the alkenes, it seems instead they are electrophiles. They accept electron pairs, right?
The same thing applies to the alkynes. They are also you said they are what?
Electrophiles. They accept electron pairs.
Alkenes.
Yeah, I'm talking about alkenes.
No. Please don't go and make that mistake. Alkenes are nucleophilic, the same way alkynes are nucleophilic. Okay, what makes them nucleophilic is because of what? The presence of the pi bonds, which contains pi electrons. And these pi electrons are readily available in both cases. So that makes them what? Nucleophilic in nature. You can see that of the alkynes on the screen now, written there. So please take note of that. Okay.
Okay.
Hello, Doc.
Yes.
Please, I want to add something small to what our sister said.
Okay.
Yeah, when you pick the alkenes, they have double bonds where we have the sigma bond and then the pi bond. But when you come to the alkynes, we have triple bonds where we have only one sigma bond and then two pi bond, which make them prone in addition what reaction. That is why they are more reactive than the alkenes.
No, what the Kekele said is what you are saying is different. She said that the alkenes, the double bonds are more reactive than the alkynes, which I agree with her, and she gave a reason. Then I'm adding up. What you are saying is the reverse. And the argument I was telling you is that yes, the alkynes have two pi bonds, so you expected them to have been more reactive than the alkenes, which has only one pi bond. But interestingly, in the case of the alkynes, okay, the bond is stronger than that in alkenes, and the bonds are shorter in terms of length than that in alkenes. Now, due to the hybridization in alkynes, there's two pi bonds, which is in alkynes, and that we expected them to have made them more reactive. The electrons there are closer to the nucleus of the carbon. They are closer to the carbon kernel. So we have protons in there, and you know protons are positively charged. So the protons will be more attracting the electrons, and that's making them not easily available, even though we have more of the pi bonds in alkynes. I don't know whether that makes sense. This is hybridization. Maybe you go and read more on hybridization, and then you appreciate this point. Thank you. So all the reactions that we are going to look at, we've seen, I think, one or two of them that will be new, but then most of them are the same as we saw in alkenes. So we wouldn't waste much time. So the first one is addition of halogens, and this one, when we saw alkenes, we said alkenes can react with bromine carbon tet, and then it's a test reagent for unsaturation. Since alkynes too are unsaturated, then they also react with what? Bromine in carbon tet. In the case of alkenes, we said that what will make you know that the bromine in carbon tet is reacting with the alkene is the fading of the brown color of bromine, the decolorization of the brown color of bromine. In the case of alkynes too, if you are in the lab and you put alkyne in a test tube and you add bromine carbon tet, with time, you see that the brown color of the bromine will begin to fade away. That tells you that there's a reaction between the alkyne and then the bromine in carbon tet or the bromine water. Again, because we said alkenes are more reactive than alkynes, if you have two test tubes and one contains an alkene and one contains an alkyne, please, this is a practical illustration, so pay attention. I like asking application questions. You have two test tubes. One contains an alkene, one contains an alkyne. You dip 2 drops of what? Bromine in carbon tet in each of the test tubes. And you time yourself. Within a matter of 1 minute, the brown color of the bromine in one of the test tubes has faded and is colorless. But the other test tube, it went beyond 1 minute. It took about 5 minutes before we saw the decolorization or the fading to colorless. The question is, which of them contain the alkene and which of them contain the triple bond? And of course, the one in which the fading took just a shorter time, 1 minute, is the one that contained the alkene. So in both cases, they are all going to react. In both cases, the brown color of bromine will fade away. But because the alkenes are more reactive than the alkynes, the fading or the reaction of the bromine with the alkene will take place very fast. While that of the alkyne will take a bit more time, okay, to also complete. I hope that is clear.
Yes, sir.
Yes, sir. Doc, I beg, can you come again on the same point, please?
Just read what is there on the screen now, and it even confirms our earlier discussion about the reactivity of alkenes and alkynes. You people, you have a lot to do. Let me go ahead so that we can finish today. or you fix another time for us to meet.
Exactly.
I requested this thing after our meeting at the 3rd week that we should have even had a meeting to finish the alkynes so that today would have gone ahead with the aromatics. I never heard from the class, and here we are in our final meeting. So after this,
So
whatever we get to,
we made
please.
the arrangement. We made the arrangement, and we expected you on last Monday, but we don't know what happened. We didn't hear from, because in our group we heard that Monday there will be lectures with Dr.
So that should have been communicated to me. You see, I gave this thing to the class that please, you are amorphous group. People are doing biology major, chemistry, physics, and other things. And then you have other education courses. So I wouldn't wanted to be so strict with the time. So I had wanted you to discuss and then pick a time that majority of you would have been convenient for you. And then you communicate to me.
Sir, please, the whole thing is, you see, we have various centers, and some of the centers, they are fortunate to have face-to-face, whilst others too, ours are only online. And it seems we are all in one group. We don't have a group where it's only for online members. So it's like those in the those who normally go for face to face, and they are the ones who that we have our course rep to from. So at times they make preferences too.
First is so those online people, solely online people, they are even more fortunate than those who have the opportunity to do face to face. Okay, I wish. They probably would have wished that they are also in your shoes. They are having fully online. So don't say that they are more fortunate. You are even more fortunate than them. Okay.
Is that
just believe Festus.
Unless you experience something.
Festus does not so.
Festus does not know that he doesn't know that he's more fortunate than any, those who are doing the blend. Okay. Anyway,
I am also in the shoe of Festus. Doctor, we are not fortunate to.
Doc, for me, I wish I could even hold your clothes. I could hold your clothes. Said this thing. Go over. Said this thing.
Hold on. So I think based on this concerns, okay, I'm even making a proposal to code so that the online group, the solely online group, you probably will need more contact hours than the 4. Okay. So please, apart from this meeting, I'm going to reach out to them for me to have another engagement with you before your quiz and then exams. Okay. I will use that one solely for tutorials with you. We solve questions. Is that right?
Yeah.
Fine. But then I, as the coordinator for the course,
as
the coordinator for the course, the last time I checked from the other tutors I've appointed, one, it seems to me that you are even ahead of them. Those who do the blend, the online and then the face to face. It seems you are even ahead of them when I go to them for updates. And I remember when I shared materials for them to finish this weekend, they tell me that it's a lot, it's plenty, and that they have not even gone anywhere with the alkynes. So how can they finish alkynes and then finish the aromatics? So you are not doing bad, and so just stay focused, and then you will be fine. Okay. Festus can be the rep for the online group.
Yeah, that's what I wanted to say.
Yes,
so you can pick my number You can pick my number
Okay, sir, your
0242
number.
0242516688. And our contact numbers have already been captured even on the schedule. You know, the course coordinator and then those who are teaching. You know, our names are there, our contacts are there.
Thank you.
So you can even get it there as well.
Yes. Thank you, sir. Thank you.
Please don't be afraid, you'll be fine, okay?
Amen. Amen.
Okay, sir.
All right.
Thank you for the assurance. But I said, after talking,
the triple
he has
bond.
just said.
The
Thank
triple
you, sir.
bond
What to make is.
So the triple bond is less reactive than the double bond because it is less nucleophilic than the carbon-carbon double bond. And why it is less nucleophilic is what I was trying to explain to you, that the pi electrons in the triple bond are being attracted to the protons, the carbon kernel. So it doesn't make them readily accessible, and that makes them less nucleophilic. But then the pi bonds or the pi electrons in alkenes, they are readily available because they are not so close to the carbon kernel and they are not being so attracted to the carbon nucleus, and so they are really available. That's why the double bond is more reactive in that instance. So if you have an alkyne and then you want to reduce the triple bond to a single bond, you need 2 moles of the reagent, okay? For an alkene, just 1 mole of the bromine carbon tet will reduce it to a single bond. But for the triple bond, you will need 2 moles. First, if you add 1 mole, it will reduce the triple bond to a double bond. Then you have 2 bromines getting attached. Then when you add another 1 mole of bromine, then the double bond also get reduced to a single bond. Then another 2 moles of what? Another 2 bromine get attached. Then you get the tetrabromoalkane. So in an exams, if I give you an alkyne,
Please mute yourselves. Please mute yourself.
that is when it comes to online lectures involving family people. We are all family people, you know. So whilst we are learning, we are bathing our children at the same time. Whilst we are learning, we are in the kitchen cooking at the same time. But it is well, you succeed. All right.
Amen. Amen.
So I was saying that in if I give you an equation whereby there's a triple bond, and then you see only bromine in carbon tet, 1 mole, okay, just 1, then you should know that the answer to give should be this one. Because 1 mole will not reduce the 2 pi bonds in alkynes. It will only reduce 1 of them. But when you go ahead and add another 1 mole, then you reduce the other pi bond to a single bond. Then you get a tetrabromo compound. So if I give you the alkyne, and then you see 2 moles, 2Br2, 2 moles of the bromine, then that one, the product should be this one straight away. Should be the tetrabromo alkane straight away. Then also in alkenes, I'm sure you remember McConaughey's rule. We saw in alkenes that when you are adding a halogen acid to an asymmetric alkene, the hydrogen from the acid goes to the carbon with more hydrogen, and then the halogen goes to the other carbon. And that we're saying is McConaughey's rule. And then we got to know the significance of this rule, because anytime you are adding a halogen acid to an asymmetric alkene or alkyne, there is an intermediate carbocation. So it is when you follow McConaughey's rule that you get the most stable intermediate carbocation. And when the intermediate product is very stable, then you expect the final product also to be stable. And I think I've talked about stability and product formation. That in chemistry, if a product is not stable, little will be formed or it will not be formed at all. And that we call it the minor product. But if the intermediate is stable, that means the final product will be stable. And when the product is stable, then more of that product gets formed. And then you get the predominant or the major product. So McConaughey's rule always leads to the formation of the most stable product, and that is the major product. And then we saw in our Kings that if you are not interested in forming the major product, that's McConaughey's product, and then you bring a peroxide, then the anti-McConaughey's product, which should have been the minor product, becomes your major product. So alkynes react with ACl, HBl to form the haloalkenes or geminal dihalides, depending on whether 1 or 2 molar equivalents are used. Again, for an alkyne, if you use 1 mole of the halogen acids, you form the haloalkene. Unless you add another mole, then you form the geminal the geminal dihalides or the vicinal dihalides. So that is that for that. So anti-McConaughey's addition, that is where you want the minor product. You want the anti-McConaughey's product, which is the minor product, to be formed more. So what you do is that then when you are adding the halogen acid like HBl, you should do that in the presence of what? A peroxide. When you bring peroxide, then the reaction favors the anti-McConaughey's rule or the anti-McConaughey's addition. So instead of the hydrogen from the acid coming to the carbon with more hydrogen, it will rather go to the carbon with fewer hydrogen, and then the halogen will go here, and that is the anti-McConaughey's product, which will be the major product. Because of the peroxide, without the peroxide, it will follow McConaughey's addition. The common peroxide we normally use is hydrogen peroxide, H2O2, or sodium peroxide as well can be used. Then this reaction, hydration, we saw hydration in alkenes. There's also another hydration in alkynes. Okay, in alkenes, we were able to add water to an alkene, but then there was a condition, and the condition is that there should be an acid catalyst or an acidic medium before you can add water to an alkene. And I gave you the reason why water cannot be added to alkene directly, because the alkene is nucleophilic, the water is nucleophilic, so there's no way you can add 2 negatively charged species together. There's no way 2 nucleophiles can react. In chemistry, for a reaction to take place, there should be a negative and a positive center. There should be a nucleophile and there should be an electrophile. So water being a nucleophile, alkene being a nucleophile, they couldn't react unless an acidic medium, so that the alkene will first react with the acid and form the intermediate carbocation, which is an electrophile, a electrophilic species. Then the water, which is nucleophile, can then attack. Then you form your alcohol by generating back the acid which initiated the reaction. The same way in alkynes too, because the alkynes are nucleophilic and water is nucleophilic, you cannot add the water to alkyne straight away unless you do that in a system, a catalyst system. And the catalyst is what? Sulfuric acid in mercuric sulfate. Sulfuric acid in mercuric sulfate. So the hydration reagent is water in H2SO4, HgSO4. Okay, so in this catalytic system, water can be added to what? An alkyne. And anytime you do hydration of alkyne, you form a carbonyl. And we have 2 types. You either form an aldehyde or a ketone. You either form an aldehyde or a ketone. Whether you form an aldehyde or a ketone is dependent on the starting material, the alkyne that you are using. But let me give you a layman's perspective here, how to know the product. You see, the triple bond is between 2 carbons. So if you are doing hydration, what you do is that you reduce the triple bond to a single bond, then to one of the carbons which initially bear the triple bond, you bring double bond oxygen on it, as you can see, so that you form the carbon. Then when you do that, then the other carbon, which bear the triple bond, you add 2 hydrogens to it. So if I bring my double bond oxygen on this carbon, then the 2 hydrogens should be added to this carbon. If I bring my double bond oxygen on this carbon, then the 2 hydrogens should go to this carbon. And like I said, depending on the nature of the alkyne, you either will form an aldehyde or a ketone. This is the only reaction of alkynes that involves an inner intermediate. All the reactions that we were talking about in alkenes and even in alkynes, there is the intermediate carbocation, which we know the stability of carbocation. I've explained to you already. But for this particular reaction, it does not involve a carbocation intermediate. The intermediate is what you can see here, enol, an enol intermediate. Please go and get to know the difference between a phenol, an enol, and an alcohol. Know the difference between a phenol, an enol, and then an alcohol. All of them have the OH. Okay, but then go and find out the difference. This is the mechanism. Nobody will ask you to show the mechanism, but then it's just for you to appreciate what is happening. When you add the water to the alkyne, you form the enol intermediate. Now the enol intermediate, the oxygen has a hydrogen, we call it the alpha, then the beta, and then the gamma. So the hydrogen on the oxygen, which is the alpha, it must be shifted all the way to the gamma position. So when we remove this hydrogen from the alpha, you bring it to where we have the gamma. There are already 2 hydrogens there. So when you bring the other one, it becomes CH3. Now, the double bond on this hydrogen then breaks and form a double bond oxygen here. And then the carbon double bond here of the enol will also break and pick on that hydrogen here onto this. And then you form this. We call that one the alpha gamma shift. So that leads to the formation of what? This product. Now, this product is an aldehyde because the starting material is a terminal alkyne. In fact, for acetylene, which is the first member of the alkyne, you always, when you hydrate it, you always will form an aldehyde. There's some terminal alkynes, like 1-butane, you form a mixture of products. You form an aldehyde and a ketone. But for all the internal alkynes, you always will form a ketone. You always will form a ketone. Then hydrogen cyanide is the same as the addition of the hydrogen acid. Okay. I'm sure we all know of this particular component of our paint products. You know, some paints we call it the acrylic paints. Okay. There's an organic compound that is used in preparing this acrylic paint. We call it the acrylonitrile. Okay. So when hydrogen cyanide reacts with an alkyne, you form what? An acrylonitrile. A very, very important material that is used in the preparation of what? Acrylic paints. Acrylic paint. Then this one, hydrogenation. When you have a double bond, you can add hydrogen in the presence of a catalyst and you form an alkane. The same way when you have a triple bond, you can add hydrogen in the presence of a metal catalyst and you form an alkane. So because the triple bond, there are 2 pi bonds, it means you will need 2 moles of the hydrogen. If you add only 1 mole, you form the alkene. It will reduce the triple bond to a double bond. Then when you add another 1 mole, the double bond also gets reduced to a single bond. So if you want the alkane straight away, then you need 2 moles of the hydrogen to be able to convert the triple bond straight to what? An alkane. So these are our examples here. When you add 1 mole first, it will reduce the triple bond to a double bond. When you add another 1 mole, then it will reduce the double bond to what? An alkane, single bond. So if you want to convert a triple bond to an alkane direct, then you need 2 moles to do that. That's hydrogenation, reduction reaction. Any question? Any question, please? Yes, yeah. Go ahead.
Sir, it's an old hand, sir.
Okay, then lower it and then let's move on. Any other person? Okay, so now, if those of you, Joseph, are you asking a question? If not, mute yourself.
Yes, sir.
Okay.
Yes, sir. I want to ask a question. Okay, my question is that on the account when you are adding water and then the acid, you explain that the pipe will take to
Joseph, I hardly hear you. Your voice seems to be very far away.
Hello, sir.
Yeah, it's better now.
Hello. Hello.
Better now.
Oh, okay. So what I'm trying to find out is that is it a double bond when you are adding water? The double bond shifts from the carbon-carbon triple bond, and then it forms between the carbon and then the oxygen. So my question is that by what process, like how the process that the bond moves from the carbon to the carbon and then the oxygen, because from the alpha you come to the gamma and then this one.
So
please, you get me?
Yeah, so that's what I'm telling you, that there's some shift. Okay, the process is what? There's a shift. That process you are talking about is what we call the alpha gamma shift. Okay, you see, on the oxygen there's a hydrogen, so the oxygen is labeled as what? Alpha. So the hydrogen on it is alpha hydrogen. Now we are saying that that hydrogen on the oxygen is being shifted from that point to where the gamma is. And where the gamma is, there are already 2 hydrogens there. So if this one go and add up to be 3, so you get CH3. Now, in shifting the hydrogen from the oxygen to the gamma position, this bond then breaks and form a double bond with the oxygen. Okay, the carbon double bond oxygen. And you know, carbon should always have 4 bonds. So then the carbon-carbon double bond will also break and pick on the hydrogen onto the gamma position. Now, this particular process is the alpha gamma shift. Now, if you look at the intermediate, it is an enol. Enol intermediate, that's the functional group. And then the final product is what? A ketone. Sorry, a ketone functional group. So there is even a type of isomerism here. And then that is called the keto-enol isomerism. Okay, so this particular reaction leads to another isomerism we call the keto-enol isomerism, because just look at the intermediate. Okay, how many carbons are here? 2. How many hydrogens are here? 4. Oxygen is what? 1. When you come here, 2 carbons, 4 hydrogens, 1 oxygen. So this enol and then this keto product, they have the same molecular formula, but then they have different structures. So they are isomers. And the type of isomers is what we call the keto-enol isomers. In other jurisdiction, the rearrangement of the enol form to the keto form is what we call the tautomerism. So again, the two products here are said to be what? Inokitototomers. So if you have heard of that phenomenon, then we are seeing it here. Okay. So that is an answer to your question. So I was here, and then I was going to tell you that when you have a triple bond and then you add 2 moles of the hydrogen, you go and get the alkane straight. If you add 1 mole, you form an alkene. But we all know that alkenes exhibit geometric isomerism, cis and trans, or the EZ. So if I want to add 1 mole of hydrogen, okay, and form a normal alkene that will not show cis and trans, then the catalyst can be platinum, nickel, palladium, palladium. Those normal reduction reaction of alkenes to alkanes where we use the heavy metals as catalyst. But if I want the alkene that I'm forming to be the cis or the Z isomer, geometric isomer, then there's a particular catalyst I need to use. There's a particular catalyst I need to use. Please hold on, give me about 10 seconds. Give me a minute, okay? I'll join the class soon.
Please, this slide that he's sharing right now, has he shared it to the platform?
Yes, it's on the platform.
Is it the same as the alkane? How will I put it? One on the platform.
Please, if I will beg that if you have the slide, you can reshare it to the page. Because of the too much chatting in the biochemistry page, sometimes you are not able to get those slides.
They just said it on the page. They can see now. They just said it. Please.
That's why I'm asking whether there are too many slides that are there.
Okay, so this first just talking. Can it be possible that we also create a new group where all those having it solely online will join? Would that be possible?
Yes, that is also be good because the one we have is for all of us.
So that totally online. Let it be one after the other. Okay? Let it be one after the other. I can't hear what you're saying.
Please, it's recorded, so let's wait. Maybe
I said go to the group and put the link in the chat so that you can in the group. The link, but that's
yeah. First,
When you create a group and then put your link, you see all those. Even if you are not in that line, you can easily join. You can equally join. So one person can be maybe at UCC or West Coast Center, and at the same time to join the online.
then whatever, then first you drop your number, then we will give you high, then you add those of us who are slowly online. So you give us your number, then if you hire you, then you add us.
yeah. So can you press the number in the chat person so that we put it up there. We give you a high, then you add us onto the platform.
So first of all, let's set up your
I would suggest that we have a created solely for the slides, so that it will not be with contributions and other.
Actually, if we form that online platform, we can always say there's no need for too much backup.
It should be solely for the slides, so that anytime we want to make reference to the slides or when videos are being uploaded and they are available. So that group should be solely for materials, no contributions,
Yeah.
no except the slides and the videos. So that
Yeah. So your number. Take your number.
Okay, my number is 0241. Those of you asking for my
Hello.
number.
Hello. Yeah, I'm back.
And let me. Okay. Say it back. So when he's done, okay, continue.
So if you are adding 1 mole, I said if you're adding hydrogen to an alkyne, a triple bond to form an alkane, you need 2 moles of the hydrogen. Now the catalyst is the normal metal catalyst. It can be nickel, it can be platinum, it can be cobalt and others. But if you are adding 1 mole of the hydrogen, then you know that the triple bond will be reduced to only a double bond. And you know the alkenes can undergo the cis and trans isomer. So if you want the cis or the Z, as you can see on the screen, see that the 2 hydrogens are pointing to one side, and then the 2 ethyl groups are also pointing to the same side. So this one is the cis or the Z, 3-hexene. If you want this particular isomer, so that the alkene will not be the normal one straight chain without showing the geometric isomers, then there's a catalyst that you need to use. Now the catalyst is what you see there. You see you have Ni2B into bracket P minus 2. So the P minus 2 catalyst nickel boride, okay, when you use as your catalyst, will give you the cis or the Z isomer. Take note. Then there's another catalyst which can also give you the cis or the Z isomer, and that one is the Lindless catalyst. The Lindless catalyst. It can also give you the cis or the Z. So the Lindless catalyst is this one, palladium / calcium carbonate in quinoline. Palladium / calcium carbonate in quinoline. That one also give you the cis, as you can see here. But if you want the trans alkene or the E alkene, then the catalyst that you use is lithium in ethyl amine followed by ammonium chloride. Lithium, ethyl amine, ammonium chloride. So in an exams, whatever I do to test you here is that I will bring an alkyne, maybe 3-hexane. Then I will be adding hydrogen, maybe 1 mole of hydrogen. But then the type of catalyst I will use will tell you whether it is a cis alkene that I want you to draw, or it is a trans form, or it is a normal alkene. So pay attention to the various catalysts and then the type of isomer of the alkene that they will give. Then we are looking at the last but one reaction of alkynes, and this reaction is for only the terminal alkynes. The terminal alkynes that have terminal hydrogens, we can remove the hydrogens and then extend the chain. So when you add a base like molten sodium, you form the sodium metal replaces the hydrogen, and then there's evolution of what? A hydrogen gas. When you have that intermediate and then you hydrolyze it, then you form your alkyne back and then sodium hydroxide. Take note. But then again, this is the last reaction of alkyne, which is also very important. This particular reaction is a test reagent to distinguish between terminal alkynes and the internal alkynes. So you have a triple bond. One of them, the triple bond is at the end. The other one, the triple bond is in the middle. How do you distinguish between the two? And this is the reagent that you use: ammonical silver nitrate solution, or the copper's chloride, what do you call it, silver or copper's chloride solution. Now, terminal alkynes will react, but then the internal alkynes will not react. Now, in the case of the ammonical silver nitrate, the silver metal from the reagent will replace the terminal hydrogen, and then there will be a precipitate forming. That is what we call the silver mirror PPT. Okay, the silver mirror PPT. When the silver metal replaces the terminal hydrogen, you see that there's an arrow pointing down. In chemistry, when you write an equation and then the product that is formed, you will see an arrow attached pointing down. It signifies what? PPT. It signifies formation of what? PPT. And if you were to be doing this one in the lab and you are doing it in a test tube or a beaker, you see that when you have a terminal alkyne like ethine, like 1-butane, and you add ammonical silver nitrate and you swirl it, you shake it, for some time, you see that the walls of the test tube or the walls of the beaker, you see that it is showing some kind of shiny precipitate, which we call the silver mirror precipitate. And that tells you that there's a reaction between the ammonical silver nitrate and then the terminal alkyne. If it is not a terminal alkyne and you add this ammonical silver nitrate solution, you will not see any silver mirror PPT. There will not be any reaction. And that will tell you that that alkyne is not a terminal alkyne, but it is what? An internal alkyne. So this particular test reagent is used to distinguish between a terminal alkyne and then an internal alkyne. Example, 2-butane and 1-butane. If you are in the lab, chemistry lab, and you are giving 1-butane and 2-butane to perform a simple chemical test to distinguish between them, you can use the ammonical silver nitrate test. The 1-butane will react, which will lead to the formation of the silver mirror PPT, and then you can write this equation down here. But then the terminal alkyne, the 2-butane, will not react. So then you can then distinguish between the two. If you don't use the ammonical silver nitrate, but you are using the copper's chloride, that one, you will not see silver mirror PPT, but then you see a reddish brown precipitate, okay? Reddish brown precipitate. This alkylation is what we saw earlier on, that when you have a terminal alkyne, you can elongate the chain by reacting the terminal alkyne with a base, followed by adding an alkyl halide. So depending on the kind of chain you want to elongate the terminal alkyne with, then you choose your alkyl halide appropriately. So this one, we've already touched on it, so there's no need of me wasting time on it. Like the alkenes, we said oxidation cleavage. If it is mild oxidation, you form a diol when we're dealing with the alkenes. If it is exhaustive oxidation, it breaks the double bond and you form an acid or a ketone, depending on what? The nature of the alkene. The same way alkynes, the triple bond can also be cleaved, okay, through ozonolysis or exhaustive oxidation using KMNO4. In both cases, for an alkyne, when you cleave the triple bond, okay, you are forming two fragments. You cleave it here, you are forming two fragments, and both fragments will form an acid, a carboxylic acid. Both fragments will form a carboxylic acid. So take note of that. These are typical example. So this one, you cleave here, and then you form this. But this one, there's a terminal alkyne, so when you cleave it, you form an acid and then carbon dioxide. So that brings us to the end of alkynes. Please, yesterday evening or night, I shared the lecture slides on the aromatics. There are about 4 slides. I hope you have seen them.
No, sir.
No, sir.
Please.
The chemistry major student,
No,
please
sir.
push it to the main page. I share it on the chemistry major page yesterday night. about 4 different slides on our aromatics. Please, one of you can push it on your main page so that the biology major and then the physics major can also get access. So I'm going to start with aromatics, but I will wish that we take some few minutes break, and we come back and then we start the aromatics. So please, we are giving ourselves 15 minutes. Don't go far. Just stretch your legs and then attend to your husbands, your wives, and then your kids for just 15 minutes. Take some water or take some cocoa, and then we are back in 15 minutes time to begin the aromatics.
Okay. Hey, enough for more, Charlie.
Thank you, sir. Hello.
Yeah.
Hello.
Festus,
So
we can
back
hear
to
you.
back to the conversation, Charlie. The way Sister Kafu being our class rep for, let's say, biology major, senior was here coining, and now they are having a very strong team for, let's say, UCC center. And in the sense that they even have a colleague who normally stands out to teach. I think we those having it solely online too, we also equally have to come together. In fact, this thing, me, I'm always lost to this chemistry thing. I don't know. I did chemistry
Yeah.
too, but this thing,
Come on.
I'm always. So I think we also have to form a strong group
Wait,
where we
Festus,
can
bring your number. Festus, give us your number. Festus, give us your number now.
0241
First was number 20 intro. Okay, Bobo.
0241
Okay.
62
Okay.
3756.
Please, you can just send it to the comment, the chat section, so that everybody will get it.
Okay.
Just type it in there. I'm waiting there.
Only no crana na waka no ya waka no de eye no kro do I second. And yes I found the master we get my chemistry. The way I am see Jimmy Moody na after the say what's up
Please, some of us we don't
So the
understand
number,
you.
so the
Yeah,
number is going to send be the administrator for the online, right?
Senior Festus was suggesting that we should form a strong group, and I said I
Yes.
second.
So this thing. Hello, sir. Please, I've sent it. I've sent it to the message line. So that we can also have this peer teaching. This peer teaching, and we are supposed to do something to help ourselves. And it's not
because this chemistry
The
past question.
one the noise, the noise be plenty too much.
please reduce the noise so that we talk this chemistry thing because yes, Remo, if you know that you are not talking, mute yourself, then let's come together and then find solution to this chemistry thing. Yes,
Now, please, may I ask, among us, is there anyone who can? Last Sunday we had some from UCC Center. Someone came in that was a peer teaching. Is there anyone among us who can stand out to help us in that way? That the person should be good in projecting. That's how do you call it? Presenting this thing like the way the lectures do and the other stuff. Is there anyone among us who can help us,
In which
especially on
aspect
this
are you
thing?
talking?
I said, now when we form the group, we should have the opportunity to do what is called peer teaching. So that one we all come in one accord. Maybe this day, this time, we are doing this, and with that, we have to get someone who will now be our lecturer. Like that, that's among us. We call it peer teaching. So I'm asking that is there anyone who can help us in that manner, especially with the chemistry, and even not only chemistry, all the other this thing. Because if you are coming together to be a group and then you be studying online, we can do it across all the 5 courses that we are reading.
So currently, you are dealing with only the chemistry or all the subjects, all the courses you are doing.
Say if the group is a duly formed well, we can do it for all, because both chemistry and biology, it seems we are all doing one course for this semester, block one, introduction to organic chemistry, those being in major, that's biology major, biology friends, the chemistry major, we are all doing one. Organic whatever, the organism, it's also one. You see, it's also one. Then the other side will also come. That is
Oh,
the core will
so
come.
who is that?
That is the nature of science, the psychology, and then the curriculum. That one too will also come.
First of, I saw echo what would you need to check your mind.
Please, me, I can help with the curriculum.
Okay.
Curriculum biology.
Festus, let me bring a suggestion. You know, this platform, we are recording it. This platform, we are recording whatever we are doing. So I think you should create the group. Then we discuss all this thing. Because this thing, they are going to put it on the internet and then it is being recorded. So you create the group, then let's do that discussion there, because the UCC Center, they didn't do any discussion on this platform. They created the
Thank
group. And they did their
you.
lesson. Because
Okay.
this is being recorded.
I've heard you, sister. I've heard you. Thank you very much.
Please, let me also bring my suggestion. I think as we are all
Please,
online right now, the link should be recruited right now. Share the link in the comment section for us to join. That would be a better option, I think.
oh, okay.
Mohammed, please, it looks like if you are sharing your slides, so please take note.
Please, colleagues, has the link been
Why?
created?
No, I don't.
I went offline.
Why? Is the teacher time? Is the doctor time?
Please, I'm asking whether the link is created.
No,
They need
no,
information.
no, please. Christmas is not creating the group. Then later you send the link into the chat. So let's wait for the link for you, okay?
All right, thank you.
Hello. Are we all back?
Yes, sir.
So we're starting with the aromatic hydrocarbons. We had earlier on classified hydrocarbons as aliphatic and aromatic. And aliphatic, we talked about the saturated aliphatic, which is the alkanes, the unsaturated aliphatic, which is the alkenes and alkynes. And we have exhausted everything in this part. So we are only left with the aromatic hydrocarbons. Now, the aromatic hydrocarbons are enormous, they are a lot. But as far as this course is concerned, we are supposed to limit ourselves to only the benzene chemistry. And then we will then we'll look also at their structure, their naming, their reactions, and then the side reactions, and then the applications. We also talk about aromaticity. When we say a compound is aromatic, what does that mean? Okay, what are the criteria for aromaticity and all that? So we are to look at that. Now, the most common aromatic compound is benzene. The most common aromatic compound is benzene. Aside benzene, we also have other aromatic compounds. Please just be very mindful about my choice of words. There is a difference between aromatic compounds and the aromatic hydrocarbons. Here, I'm talking about aromatic compounds in general. So other common examples of aromatic compounds, we have benzoic acid. I'm sure you can see my screen. Benzoic acid is here. We have vanilla, the lovers of ice cream, you know, one of the flavor of ice cream, that's the vanilla ice cream. We also have acetyl salicylic acid. We have essential oils, okay, from plants. Essential oils from plants. Most of them contains aromatic compounds. Those of us who normally eat orange, you know, the orange peel. When you peel the orange, the peel, when you squeeze it, you see that there's some kind of watery, oily substance that comes out. All those things are aromatic compounds. And they are very, very medicinal, and they have a lot of uses. So, aromatic compounds, you could see they have the aromatic nucleus, but then you are also likely to find other elements other than carbon and hydrogen only. Some of them, like benzoic acid, has what they call it, oxygen. Vanilla has oxygen in it. If you take aniline, it has nitrogen in it. If you take phenol, phenol has oxygen in it. But we want to narrow ourselves from the aromatic compounds to aromatic hydrocarbons. Aromatic hydrocarbons. And when we talk about aromatic hydrocarbons, we're going to talk about aromatic compounds that contains only carbon and hydrogen. Okay, that contains only carbon and hydrogen. Nanache, your hand is up. Is there any challenge? Nanache. Hello. Why is his hand up? So,
maybe it's a mistake.
Aromatic hydrocarbons are unsaturated ring compounds that resist the typical addition reactions of aliphatic unsaturated compounds. Instead, they undergo substitution reactions. And the reason why these aromatic hydrocarbons do not undergo the typical addition reactions like we saw in alkenes and alkynes is because of their high stability. They are very, very stable. And because of due to this high stability, they do not undergo the typical addition reactions where we could add bromine carbon tet, we could add hydrogen and a metal catalyst, we could add halogen acids. Those ones, aromatic hydrocarbons, do not undergo these addition reactions. Rather, they will prefer to undergo aromatic substitution reactions. Aromatic substitution reactions. Examples of these aromatic hydrocarbons is benzene, naphthalene, and anthracene. Please give me a minute and I'll join you soon. All right, so examples, as you can see on the screen, we have benzene, naphthalene, and then anthracene, okay? And our focus is going to be on benzene alone. For the chemistry major student, they will be doing other chemistry courses with me, which we will be looking at naphthalene and anthracene and other aromatic compounds, you know, in detail. But because this is an introductory course, we will focus on only benzene. We'll focus on only benzene. And I'm sure we all know benzene, and we know the structure of benzene. So that is benzene, its structure. You see, this is a calculate structure of benzene, and then this is the resonance structure of benzene. Now, a little history about benzene. He has the formula C6H6, and the first person to propose a structure, a chemical structure for benzene was Dewar. Dewar proposed 3 different structures for benzene, and but later, Kekule came out with his experiment, which gave us an idea about the structure of benzene as a cyclic compound with 3 pi bonds alternating with single bonds. Okay, but then Kekule structure, though, is still in use. Kekule structure, although is still in use, did not address one thing. It's as if though he meant the pi bonds were static also. I was going to register, but he said without the utility bills, I can't register. So I was going to come and explain this. So that's there's nothing to explain. So please come back. I'm having an online lecture, so come back after 11:30. Okay. All right. So Kekule structure currently is still accepted. Okay. But then modern experiments later revealed that, you see, where the double bonds are in the Kekule structure, those double bonds, those pi bonds are not static. They are not rigid, but that they are in constant motion. They are in constant motion. They are mobile. And for that matter, to represent that one, we use this kind of circle inside the ring. So it's not just the typical circle in mathematics we know, but there is just this round thing here is showing the continuous movement of what? Electrons, the pi electrons, okay? And so that represents the resonance structure. So either this or that, they are both accepted as the structure of benzene. Now, nomenclature of benzene and its simple derivatives. Benzene is benzene. Wherever you go, the name benzene becomes a common name, and it's still also an IPAC name. But then when you have groups on benzene, then there's a way for us to go about and name it. And for the mono-substituted benzene, benzene itself becomes the parent name. Then the group on the benzene becomes a substituent. So if you take what you see on the screen, this is fluoro, that's fluorine. So fluoro, then you add the name benzene, so fluorobenzene. This one is chlorine, so that will be chlorobenzene. This one is bromine, so that will be bromobenzene. This one is nitro, so that will be what? Nitrobenzene. So for mono-substituted benzene, when I say mono-substituted, when you have only one substituent group on benzene, then the name, you consider the group on benzene as a substituent, and then the benzene itself becomes the parent name. So if I ask you to write nitrobenzene, you should be able to. If I ask you to write bromobenzene, you should be able to. Please, are we okay up to this point?
Yes,
Yes.
Good.
Sir, so sir, hello, sir.
Yes.
Sir, please go back a bit. So the fluorobenzene and then chloro, they are showing the resonance, and then the bromo and then the others. We are having
So all that I said earlier on is that whether it is the benzene nucleus, the benzene structure, whether you use the resonance structure or use the calculate structure, they are all accepted. So sometimes when I'm giving illustrations, I interchange them, I mix them, so that somebody will not go and say that oh, this one is the structure of benzene, but this one is not, or this one is the structure of benzene. In fact, both are accepted. But what we are saying is that the resonance structure.
And then the other name is what?
The other what?
Resonance structure, and then the other name is what?
Calculate structure. Calculate structure. Calculate structure of benzene. It was named after the what?
Is it C or K? I want to write it.
Kequle.
Okay.
With an apostrophe on the last letter E. Kequule.
Okay.
Then apart from this mono-substituted benzene like fluorobenzene, chlorobenzene, nitrobenzene, bromobenzene that I've just told you, there are some other common names of other mono-substituted benzene derivatives, which even though they are common names, but they are accepted wherever you go. They are accepted wherever you go. Okay, and that is what you see on the screen here. We have benzoic acid. Benzoic acid is a common name. In Ghana here, it's
hello,
benzoic
sir.
acid. If you go to Europe, it's benzoic acid. If you go to America, it's benzoic acid. Toluene. When you have a CH3 on benzene, it's toluene. Then when you have NH2 amino group, it's aniline. When you have an OH, it's phenol. When you have a CH double bond CH2, an alkene substituted group, it's called styrene. When you have a ketone functional group, like this one, is what? Acetophenone. When you have an aldehyde functional group, it's benzaldehyde. When you have a methoxy group, that's OCH3, it's what? Anisole. Please, these 8 compounds here, which are common names of mono-substituted benzene rings, know them off head. When I ask you benzoic acid, you should be able to draw the structure. When I ask you styrene, you should be able to draw the structure. When I ask you benzaldehyde, you should be able to draw the structure. And when I give you the structure, you should be able to provide a name. Know these ones off head, please. Yes, there's a hand up. Let me pick a question and then maybe we'll move on.
Okay, sir. With benzene with fluorobenzene. So I want to ask if maybe the substituent is on maybe the other rings or the other carbons. Are we going to have the same name?
Okay, so when there is no group on benzene, okay, any of the carbons assume position 1. Okay.
Okay, sir.
When there is no substituent, any of the carbon here can be substituent 1. So if you are bringing fluorine, it can be down here. It's still fluorobenzene. It can be here, fluorobenzene. It can be here, fluorobenzene. It can be any of the carbons, and it's still fluorobenzene. It is when you have di-substituted benzene derivative. That is when you have 2 groups or 3 groups. That is when we will get to know how to number it, to know where to number from, and then which one will be appropriate numbering system. We'll get there soon. Okay, but for now, for the mono-substituted, any of the carbons assumes carbon 1. So wherever the bromine, fluorine, nitro group is the same as what? Fluorobenzene, chlorobenzene, nitrobenzene, and whatever.
Thank you very much.
So these ones, I said you should know them. Okay, off head. Anisole, benzaldehyde, acetophenone, styrene, phenol, aniline, toluene, and benzoic acid. In an exams, you can be given all these names to draw the structures, or you can be given the structures to provide their common names. So I'm leaving it on the screen. Look at it. But beyond here,
Sir, please, the screen is not showing.
It's showing, no.
It's only your side.
Dog. Hello, dog.
I think dog has gone offline.
Okay. So my colleagues, assuming the structure is
Hello?
given like this.
Festus.
Hello, sir.
Festus, do you want to become my teaching assistant? Do you want to become my TA?
No.
Because it
No.
seems the little opportunity you get, you want hello class. Huh? Are you my TA?
No. Just full of questions, though.
Well, if you want to be my TA, that's fine. I'll be glad to work with you.
I will appreciate that, and I'm praying that one day I'll be like you say. So please,
yes.
The is it a toluene?
Yes.
Then the aniline. In case the structure is given and you have to name it,
Mm-hmm.
do you want the toluene or you want the one in the bracket? Because it seems the one in the brackets can easily, when you are writing it off, you can, because of the CH, you know that the CH is misal, you can easily look at it and you write it in. So, which one do you want? Is it the toluene, the aniline?
Okay, any one of them is accepted. So I was just trying to draw attention that what is in the bracket is more or less like the IPAC name, okay?
Okay.
And you could see that one we have for only the toluene, aniline, and then the phenol. The others, we don't even have any IPAC name for them. But what we are saying is that for this particular compounds, okay, the common names is accepted worldwide. So when we say aniline, and you go to Europe, Asia, America, everybody know aniline. You understand? Though it's a common name, it is generally accepted worldwide. So whether you write the one in bracket or the common name, they are all correct and they'll be accepted in an exams.
Yeah, Doc.
Yes, Vincent.
Yeah, please. I want to know if these benzenes are around us. In which substance can we get them?
So, Vincent, have you eaten orange before? Tangerine?
Yes, Doc.
Okay, you know the orange peel or the tangerine peel, okay?
Yeah.
When you squeeze it, you see that some oily thing comes out.
Yes, please.
It contains aromatic compounds, which includes benzene.
Okay.
And
Thank you.
there are a number of natural products that contains benzene and then other aromatic compounds. If you like, go and Google right now and then get to know the sources of sources of benzene. Okay.
Okay.
And then you will see where you can find benzene. A lot of places. Okay. Yeah. So they are all around us. In fact, when I was starting this course, I tried to relate your environment to organic chemistry. That everything around you is organic. The plants, the animals, the plastics, the plastic bowls, the books, the paper, everything around you is made up of an organic compound. So they are all over. Okay. But benzene is actually an organic solvent, which if you go to the chemistry lab, you can see some. It's very, very, very unfriendly solvent, which is advisably that those of us who have done chemistry to the highest level, or those of you who are doing chemistry, in as much as possible, you try to abstain from getting contact with benzene for continuous exposure, because benzene is carcinogenic. And for the guys, if you continuously inhale and get exposed to benzene, you can become impotent. And your wife will start having problems with you. And for the
person to shout age.
And for the ladies too, you can become infertile. Okay. So those days, but now, if you come to my research lab like this, instead of using benzene to do some work in the lab, I'll prefer to use toluene, because everything that benzene can do, toluene can do it. Okay. But toluene is a bit more friendly compared to what? Benzene. But then one thing I want you to have in mind is that every chemical in one way or other has some level of what? Toxicity. Is that right? Sometimes it is how exposed you get exposed to it over a longer period, then you start seeing its effects. But then some of them, they are very, 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 dangerous, and you are advised that next week, when you go into your lab for your practical, the practical course of this, the practical components of this course, you will be going to your various centers for the practicals. When you go to the chemistry lab and you see benzene, please just wave at it from afar. Don't go closer, okay? So that you protect your something.
Okay, Doc. I want to find out when we go to the practical centers, would they provide us with a protective cloth, or are we to provide it by ourselves?
So I was going to deal with this after the end of the class, because for those of you online, I'm telling you, but then I have told my tutors who will be meeting the other groups also to tell them. The safest chemical environment is still prone to accidents. So for us, the coordinators and then the practical coordinators, I'm the coordinator for this theory and then the practical too. I'm the coordinator. I'll be examining you on both. My point is that students should go into the lab well protected. So I am going to share with you the practical manual. It's like your Bible or your Quran. Okay, the manual is what is going to guide you when you are working in the lab, the do's and then the don'ts, and then the experiment that is in the manual. And just to give you a little gist, we've outlined the things that you are not supposed to do in the lab when you are in the lab. And we have also outlined how you should go to the lab well prepared. You need a covered footwear. Nobody should go to the lab with slippers or open shoe. For the sake of the practicals and chemistry practical, make sure that you get a covered footwear. Okay, that in the lab we don't go and do fashion there. So please, the lab is seriously for protection. Then you need your lab coat. Go with a lab coat, because the lab coat is not only protecting the clothes that you are wearing, but also your skin. Mind you, you can go to the market and buy lab coats, but when your skin gets in contact with an acid, I'm not sure you can get a new skin to buy in the market. So you need your lab coat. Then you need goggles for protection of your eye. You need goggles. Then you need hand gloves. You need hand gloves because you'll be touching chemicals, you'll be touching. The experiment is not like you're going to be a spectator. The tutors are going to do for you. No, we are, as part of the training, we want you to have a hands-on feel of this experiment so that when you find yourself in a school, a secondary school, and you are the chemistry teacher and you have to set up the chemistry lab, you will know how to go about it, how to prepare solutions, how to set up labs. So you'll be touching glasswares, you'll be transferring chemicals, they will ask you, add this to this. So you need hand gloves so that the things that you'll be touching, you are not touching with your bare hand. So all these things are captured in the manual I'll be sharing. I'll share it on the page for you to all get access before the practical day so that you even read. Somebody is asking whether you are to buy all this yourselves. The truth is that for the mainstream student, okay, there is a mechanism that we go and then they pay for it and then it's given to them. But for code, we are not yet there. So for code, we expect that you, because when you go and teach at secondary school, you need your own lab coat. You need your own goggles. So please, it is not, let me say this also here. Don't allow any tutor to impose or force you to buy anything from their end, okay? But advisably, and for your own safety, please do well and then get yourself well protected. But then for now, I will say it's not compulsory. Okay, that is, we are not going to force those things on you. But then as part of the safety measures for your own interest, I'll plead that kindly get this kind of safety apparatus. Okay. All right. Can we continue?
Yes, please.
All right. So I'm giving you a clue here. The online people, I said you have more advantage than the others. These structures that you see on your screen, okay, end of semester exams, you can be given the names, all the 8 names there, and then you'll be asked to give the structures. Or you go and see all the structures there, and you'll be asked to provide the names. So please know all the names offhand. Thank you.
Hello, sir.
Yes.
Hello, sir. Looking at
Yes.
the structure of the benzenes, it will look like is it cyclone alkanes? It's like the structure is just the same.
Okay. So we will Albert, it's a very good observation. Albert is just trying to say that if you look at the benzene, it's like an alkene, a cycloalkene with 3 double bonds. Okay, but very soon I'm going to project another slide and explain to you the difference between an aromatic hydrocarbon like benzene and a triene, that is an alkene with 3 double bonds. Okay, I will do that pretty soon. So we are done with one substituent. Okay, now when you have 2 substituents, how do we name them? So when 2 substituents are present, their relative positions are indicated by auto, meta, and para, which is abbreviated as O, M, and P. Okay. You can as well also use the numbers. So if you look at the example on the screen, we are all considering, have you seen what the arrow is pointing to?
Yes, sir.
Yes, sir.
Good. So let's consider that there is a group here. Let's consider that there's a group here, maybe a CH3, a methyl group, or an OH or whatever. Now, adjacent to it is this carbon. So if a group is here, then that group is what? Auto to it. It is auto to it. And the auto is the same as what? 1, 2. So if you number from here as 1, then here will be 2, here will be 3, here will be 4, 5, 6. So auto position is always the number 2 to the group here. Okay. An example is here. You could see that this is a bromine here, and then there's another bromine here. And if you are to number, it's going to be 1, 2. So this second bromine is auto to the first one. And that will represent with what? O. So if you want to name it, there are 2 bromines. So that will be what? Dibromobenzene, isn't it? But then the dibromobenzene, you have to bring their position. So it's going to what? 1, 2, dibromobenzene. And whenever we have 1, 2 arrangement, is the same as what? Auto. So you can also say O dibromobenzene, and that's also correct. Auto dibromobenzene is the same as what? 1, 2. The 1, 3, as you can see here, is what? Methyl. Methyl, denoted by M. So wherever you see 1, 3 dibromobenzene, you can equally say methyl dibromobenzene or M dibromobenzene. Then this is the 1, 4. 1, 2, 3, 4. So 1, 2, 3, 4 dibromobenzene is also denoted by the para position P. So you can also say P dibromobenzene. For those of you who I'm sure we've all heard of paracetamol. Is there anyone here who has never heard of paracetamol? We have all.
Oh, no.
Now the word paracetamol is because if you look at the structure of paracetamol, it is telling you that there's a group which is para to a particular functional group. So the name paracetamol came about because of this relationship, 1,4 arrangement, which is what? Para. Okay. So when you have 2 groups on benzene, please, you can use the numbers 1, 2 for auto. You can use 1, 2 or auto, 1, 3 or methyl, or 1, 4 para. Any one of them is accepted. Any one of them
Hello,
is accepted.
sir.
Yes.
First was that.
Yes.
Sir, please, the first one.
Mm-hmm.
In fact, from the explanation, if I heard it clear, you said that looking at the structure, from the top, the apex, it's if it is assumed that there is is it, let's say the bromine or any substituent there, then that part is what? 1.
Yes.
1, right?
Yes.
But the first
Yes.
one, I'm talking about the first one. Now,
yes,
considering that the bromo is in bromo 2 and then 3.
Okay. First is I think I've gotten your point. So all I'm trying to say is that now there are 2 of them here. Okay.
Okay.
But before the second one would have come, there's only 1 there. And we are saying that when benzene is there, like you can see here, okay, any of the carbons can be 1. So if the bromine is here, that is 1, then this will be its auto. If the bromine is here, this position, then down here will be its auto, or up here will be its auto. Okay. So again, have it in mind that when benzene is there, the position 1 can be any of the carbons. Do you understand? It is when you have 2 groups there, then again, one of them becomes 1. So you see, for the examples I gave here, to get a para, I made the 1 to be on top here. To get the meter, I made the 1 to be on top here. Even to get the auto, this bromine can be up here, and then the second one would have been here. Do you understand? And it's the same thing. Okay. So it's like, let me see if I can No, it can't. I wanted to rotate it. If I were to rotate it, then you see that this one will come up and then this one will come here. And it will be the same as what you are probably thinking. Okay?
Okay. Okay.
Yes.
Hello, sir.
Yes, go ahead.
Sir, please, with this benzene, when are we considering the second substituent?
You mean this or this?
The first one.
Uh-huh.
Well, you said it's on the first 1, 2. So that means that the 2, which is the bromide, the second bromide or the bromine, you are considering that one to be or 2.
I'm coming in. Let me see something. Let me help you out, okay? I'm going back to my chem draw.
Hello, sir.
Yes.
Hello, sir. Hello, please, can you hear me?
Please, we can hear you, but hold on, and let
Okay.
me attend to the already question on the listing, and then
I want to speak on that.
Okay, go ahead. Whilst I set up my. Please go ahead.
So, yeah, as my brother was saying, so to my understanding, I think that maybe for the first one, where the bromine is close to each other, that is the auto. So maybe the position of the diagram over there can be changed, but provided maybe the bromine, there will not be any space between the two bromine. Is that what you are telling us?
Yes. So please, can you see my screen now? Can you see my chem draw page?
Yes.
Have you seen benzene? Have you seen benzene?
Yes, please.
All right. So let me go back. So now, if I want to draw benzene, I come here, pick the diagram, and then insert. Okay.
No.
Then, when I'm explaining something, and you know it, and you are, is it the same question?
No, the screen has shifted a little bit to the extreme left, so it's partially same. So I
Which
wanted to
screen?
draw your attention.
You mean the
Yours?
chem draw?
Yes, please.
But we can
It's better now.
It's better now.
Yes, please.
All right. So now we have our benzene there. Now, I'm trying to draw the dibromo, the one that you people are referring to. So now, instead of where the bromine is, see where I'm bringing it. So this is the first one. So I'm bringing a second one. Coming. Have you seen the second one?
Yes, sir.
Yes,
Yes,
please.
sir.
Have you seen the second one, please?
Yes, sir.
So
Yes, please.
I'm saying that now, where this one is your one. Then this is number 2. So it is showing auto position. It is showing what? Auto. So 1, 2 dibromo or auto dibromo benzene. Now, look at what I'm going to do. Please keep quiet and listen. Look at what I'm doing.
I'm going to shift it.
I want to
rotate.
rotate. I want to rotate, so please just give me some. Ooh.
It's noisy.
Okay, please, can you see?
Yes.
Yes.
Yes, sir.
Now, what you saw first and what you are seeing now is the same thing. Okay, so you cannot say that this time around this one is not the one again. Okay, it's the same molecule that has been rotated, and I can even rotate it so that the two bromines will be pointing down, but it is still showing the 1,2 or the O2. That's all I wanted to explain.
Okay.
Okay.
Good. So let me stop sharing this and then we go back to our slides.
Calculate structure. The resonance structure. Resonance. Okay. Calculate structure and resonance structure.
All right. So I'm sure we are okay with the auto methyl para. So like I said, you see, you need to know the two and they are the same. You can use any one of them that you are comfortable with. Just that if in an exams, I tell you to draw the structure of M-dichlorobenzene and you don't know what M is or you don't know what methyl is, then that will be difficult because maybe I might not have say 1,3-dichlorobenzene. I will say M-dichlorobenzene. So you know that methyl is the same as what? 1,3. Para is the same as 1,4. And then auto is the same as what? 1,2. All right, so you can see more examples here. And then this time around, you see, I told you to be very conversant with the common names. So when you have a situation like this, you see that the substituents are not the same, like dibromo or dichloro, as we saw earlier on. We have an acid functional group and then a nitro. They are not the same. So for this one of the functional groups, you know, when you have COOH on benzene, it is called what? Benzoic acid. It is called what? Benzoic acid. So the parent name will not be benzene again. It will be what? Benzoic acid. Then the nitro here becomes what? A substituent. Now this nitro is what? 1,2 to the acid functional group. So you can say it is what? Auto position to this. So you can call it O-nitrobenzoic acid or 2-nitrobenzoic acid. And this one, again, the two groups are not the same. So now you know that, oh, benzene with an acid group is what? Benzoic acid. So you consider all this as your parent group, benzoic acid. Then the nitro becomes your substituent. And this nitro is what? 1,3. So you can say 3 nitro benzoic acid or meter nitro benzoic acid, and so forth. So where they are different two groups, know the common name for the benzoic acid: aniline, phenol, styrene, anisole, acetophenone, benzaldehyde. That's why I said that go and know those 8 names of head. These ones, these particular ones, know them. So that when a second group comes, you know that, oh, this one is a phenol. So if it is here, then if it's like chlorine that is here, then it becomes what? 2-chlorophenol or O-chlorophenol. If it is this one, we know this one is what? Anisole. So if there's a group down here, then it is meter to 8. Then it can be what? Maybe if it's nitro anisole, or if it is 3 nitro anisole. So you need to be very conversant with these names as well, and it will really help you. So look on the screen, and you have the slide. So please, now that I've explained, go and then try hands-on. Then when you have 3 or more substituents, like you can see on the screen, that one you cannot use the auto, you cannot use the mether, you cannot use the para naming. That one you have to use the numbering. And again, in the numbering, if you take the first example, the nitro groups, you see, they are all the same. So you have to pick one of them and then number clockwise and then anti-clockwise. The one that will give the numbers the least sum. So if you go this way, if you start from here, it's what? 1, 3, 5. If you go this way, it's still 1, 3, 5. Whichever direction that you start from, you are getting 1, 3, 5, 1, 3, 5. But then if you pick the second example, there are 3 nitro groups and then there's an OH. Thank you. Normal one. The normal one is okay. Yeah. Now, if you pick this one with 4 groups, then we all know that when there's an OH on benzene, we call it a phenol. So it means that this OH will become your functional group of interest. So you start the numbering from the OH. This one, you don't have to consider the nitro. Start from the OH, because an OH on a benzene ring is called phenol. Then when we start from here, then you can either go clockwise or what? Anti-clockwise, and see which one will give you the least sum. So if you're going here, it is 2, 4, 6. And if you are going anti-clockwise, it is what? 2, 4, 6. So 2, 4 says tri-nitro, because there are 3 of the nitro. So tri-nitrophenol. So that is that for the when you have 3 or more substituents. That one you can't use the auto parameter. Please, I hope that is clear.
So is it missing the benzene name? Wouldn't it be 2,4,6 trinitrophenol benzene? Something like
No,
that.
because when I've told you, that's why I said I go back and learn this one so off head. When there's an OH on benzene, we don't call it benzene again. We call it what? A phenol.
Okay.
When there's an NH2 on benzene, we don't call it benzene again. We call it what? Aniline. When there is an acid functional group, COOH, on benzene, we don't call it benzene again. We call it what? Benzoic acid. We have styrene. We have acetophenol. We have, so know this one off head, so that when you see other substituent on benzene, these ones will be your parent name and not benzene. Then you only number from the functional group here and get to know the position of the other groups. So that is that on the naming of the benzene and derivatives. We are done with the nomenclature. So now the structure of benzene. It's 11, but I think we can continue, right?
Yes, we have to.
Yes. We will do some few minutes. I want to get to a point. I have called the director for Science and Maths and ICT, education code that for the online centers, those who are doing solely online centers, they should give us an opportunity to do extra meeting after today. So an approval will be given soon. So class, decide, and then from Tuesday going, okay, let's pick a time later in the evening, okay, then do that extra so that we can finish. Yes, France Pabna, your hand is up. Any question?
Yes, sir. Please, sir, on the benzene structures, can you write them in a straight chain?
Can you draw them as straight chain?
Yes.
No, please.
They'll still be benzene.
No, please. If you do, they are no more aromatic. So that is where we are going. Okay, that is the next stage we are going. The question is, why are we calling these compounds aromatic? You see, if you are in the house and then your wife is preparing stew or soup, and you are seated in the hall, or your husband is preparing stew or soup, and you, the woman, you are seated in the hall. You are not in the kitchen, but you smell the aroma of the stew or the soup. Okay. And before you get served, your appetite is already up. Okay. The same way applies to aromatic compounds. They are scented. They have some aroma. Okay. So virtually most aromatic compounds are scented. Okay. Most of them, they have some unique smell. So wherever you are, those of you who are the biology students, you know, some plants, some ornamental plants have some unique smell. Okay, like odorata, like some aromatic plants. As soon as you get closer to them, they smell so good. All those compounds, they contain what? Aromatic. All those plants, they contain aromatic compounds. So aromatic compounds have that aroma, and that is how come the name aromatic compound was derived from. But then we will very soon go through the criteria for aromaticity so that you know an aromatic compound can never be a straight chain. Okay. Yes. So now let's briefly look at the structure of benzene. So benzene has the molecular formula C6H6, and it contains 3 double bonds. Now the 3 double bonds alternate with a single bond. So if you look at the calculus structure on the screen, you see that a double bond comes a single bond, double bond, single bond, in that order. That's what we mean by alternating. Okay, so you cannot have 2 of the double bonds continuous together. There should always be a single bond alternating with it. Then each of the carbon has 1 hydrogen each. So the formula C6H6, the 6 hydrogens are what you can see. Each of the carbons is bonded to what? 1 hydrogen, as you can see. Then we say that all the hydrogen atoms in benzene are equivalent. They are all the same. Then we say that benzene has a double bond equivalent of 4. It has a double bond equivalent of 4. What does that mean? It means that you need to break 4 bonds before benzene can get to the saturated form. So as you can see on the screen, if I want benzene to get to the open chain saturated form, I will break one of these bonds. That's 1. I'll break this 1, 2. I'll break this 1, 3. Then all the 3 double bonds will be gone. Then I'll break one of the single bonds to open up the ring. So I'm breaking 4 bonds for benzene to reach the open chain saturated form. And that is what it means to say it has a double bond equivalent of 4. So these are now the structure and stability of benzene. We initially stated that the aromatic compounds, okay, they don't undergo the typical addition reactions we saw in alkenes and alkynes. The simple reason is that they are very, very stable. They are very, very stable. So benzene is very, very stable. And we want to, somebody asked a question, can't benzene be the same as an alkene with 3 double bonds? The explanation is what is here. So benzene is very stable and undergoes substitution reaction. If it were to be an alkene with 3 double bonds, a cycloalkene with 3 double bonds, then it should have undergo addition reaction. But benzene do not undergo addition reaction. So that is one of the reasons why benzene can never be a cycloalkene with 3 double bonds. Again, benzene absorbs 3 moles of hydrogen in catalytic hydrogenation to give cyclohexene at very high temperature, which it is not the case with what? Alkene. Alkene, you only add hydrogen under platinum or nickel. You don't need temperature. You don't need temperature. But then for benzene, because it's very, very stable, it requires elevated temperature before you can even hydrogenate it. So these are all confirming to the high stability of what? Benzene, okay? The high stability of benzene. Now, so if it is bromine in water, if you add bromine in carbon tetrate, it will not react with benzene. If you do oxidation, there will not be any oxidation. If you do hydration, there will not be any hydration. If you do addition of halogen acid, there will not. So these are all the reactions that alkenes and alkynes undergo, as we saw. But then benzene will not undergo any of these reactions. Okay, so it tells you that benzene is totally different from the other unsaturated hydrocarbons, alkenes and alkynes. They are very, very stable. So it is this evident that although benzene contains 3 double bonds, okay, the bonds interact in a peculiar way that gives benzene a unique stability and inertness, meaning it makes benzene very, very unreactive in a normal addition reaction. So instead of the addition reactions, it will prefer to undergo substitution reaction. And this unique stability and inertness of carbon is what this character is what we term aromatic. Hello. All right. So, any question, please? I think you are enjoying the class, so there's no question.
Yes, also, Doc. We are really enjoying the class.
So, another question that somebody asked: oh, can't the double bond, sorry, the benzene be the same as a cycloalkene with 3 double bonds? Now, this first one that you see here, you see, we try to measure the heat of hydrogenation. If you had, this is an alkene, a cycloalkene with 1 double bond. The second one too is an alkene, cyclohexadiene, and an alkene with 2 double bonds, a ring. So for the single bond, you need 1 mole of the hydrogen. For the 2 double bonds, you need 2 moles. Now look at the energy involved. If it is only 1 double bond, you need 28.6 negative kilocalories per mole. If it is 2, you need what? Minus 55.4 kilocalories per mole. Is that right? Now, if it were to be 3, then it's like multiplying this figure by 3. And that should have given us what? Minus 85.8 kilocalories. Is that right? But then, when we do for benzene, which has 3 double bonds, we are getting what? Minus 49.8 kilocalories. That tells you that benzene is very, very, very stable. Instead of the minus 85, we are recording what? Minus 49.8. So it can be seen that benzene contains 36 kilocalories more than a typical alkene with 3 double bonds. Okay, so this is one of the reasons why you cannot say that benzene is the same as what do you call it? An alkene with 3 double bonds. Okay, so on that note, I'm now going to explain to you the criteria for aromaticity. When we say benzene is aromatic, when we say naphthalene is aromatic, when we say anthracene is aromatic, what is the criteria for aromaticity? We will pick on that one in our next meeting because we are unable to finish. So we will deal with the aromaticity, then we will deal with the reactions of benzene, and we'll deal with the applications in our next meeting. And by that, we would have covered every aspect of the course, and you should be okay. So this brings us to an end for today's lecture. I'll just take a minute, and if there are any questions, you ask. If not, let me give this important information. Coming weekend, you'll be going to your various centers to have the CHE108D. That's the practical introduction to organic chemistry. It's a practical component of this course, but that one you do it at your various centers. I'm sure they have shared the itinerary with you. UCC Center, I'll be hosting secondary, that's those from Holy Child, secondary Takrade, and few of you who will be from Kasua joining us here. And please, when you are coming, because you might not know the lab, straight away when you get to UCC, ask of the chemistry department, and then the lab will be lab C17, first floor. When you call my number, we will meet you and show you. Those of you coming from secondary and you might not know the place. The other group, please reach out to the center coordinators, and then they will give you the names of the practical tutors I have appointed to handle you. I had a meeting with all the practical tutors, and they are ready for you this weekend. I'm going to share the practical manual with you today so that you can start reading through before you get to the lab and start preparation for the practical. In the course of the week, please do well to fix an additional time and let us finish this, because I have sought permission from the director and he's going to give us the green light to do extra hours for those of you doing solely online. So please kindly take notes and then let us make up.
Okay.
I have given out tutorial and review questions, and I'm sure you are going through. In the course of the week, before you start your quiz and your exams, I will give you additional one, which will be a preparatory material for your quizzes and exams. If you are able to create the platform that you intend creating for the online lecture group, please add me there so that I can share those information with you over there easily. Thank you, and have a blessed day.
Thank you, sir, for joining us on our platform.
Paulina, Johannes,
Sir, please, from Monday to Friday, I think we have schedules on all the days with the exception of Thursday. Mondays, physics students have class in the evening, same with Tuesday. Biologists, Wednesday, then on Friday too, we have a general course. So we only have Thursday in the evening.
So we can fix it on the Thursday, okay?
Please.
We can fix it on the Thursday.
Doc, I beg. You said the Kaswa Center, the city center, you join the Cape Coast for the practicals.
Kaswa, you are supposed to go to Accra High, but over the years, we are a bit flexible with Kaswa people. Some prefer coming to UCC, and we always host them. Myself, and then my technician. But those of you who also prefer going to Accra High, you know, that you are also put to go do that. Yes.
Okay. You come to Cape Coast.
So what of Takwa? If I want to come to Cape Coast, can I come?
Or Takwa, the Holy Child, you are always coming to UCC to join the UCC center from the schedule given to you.
All right, sir. Thank you.
Welcome.
Hey, Takwa to Cape Coast.
All right, bye for now.
Takwa the phone na musu na sitika so ko Cape wa o. Ko Cape design wa.
Okay.
To Cape design wa o. Na me teta di.
I will advise that more Kaswa, so meet me about Accra because Accra is closer to Kaswa than Cape Coast.
Oh, but me, I'll go to Cape Coast.
Okay.
Accra in
Please,
Pasay.
the online group link has been shared in the comment section. So those who are not yet there, you can just.
Yes, and
then I can hear you saying.
From Takwa to Cape Coast, they be umu. Aye.
Takwa to Cape, they do. Takwa to Cape.
What that on Friday?
They say me do na mapon.
And this is a Friday, no?
Please, the online group. How can we get it?
Please, they have shared the link in the comment section. Visit the comment section and join the link.
But I have to Yana. Comment section, Hana. And I main group, no.
This one,
hello.
This one.
But me like soon as I'm back. Me will like it. But
this particular one, just visit the comment section and you see there.
And I'm saying that I went off, so the link cannot be seen. Please share it for me.
You went off. Just go to the comment section. You find it.
It's not there. Online is
now
bound.
It's not there.
The moment you come back, you can't see any message again. Yes.
Someone should resend it. It has been sent.
Okay. Yeah, it has been reshared. Ole,
Please, so are we meeting now? Are we meeting now? If I may know.
We have biology at
yes. So what time are we supposed to
We have
biology at
Yeah, so we have biology now. So what time are we supposed to meet? On the link shared.
The whole time
Festus.
We talk about Mount
Lizzie.
Yes. Yes. What's it?
I'm trying to join the group.
Okay, but it seems that your hands have been raised.
No. I'm still on it.
Because I'm a copy, and I'm the copy in you.
One was another copy. We don't tell me use the phone, no. Me use the laptop in time my stuff.
Laptop is easy to copy.
But ukoja phone so container. Ade beti ni atini na akọ.
Who's me the baby? Me that's no China.
Yes.
Ruth.
Yes, sister. Yes, sister.
Me that's no.
Yeah, thank you.
Hey. Hello. No operation. Amanda.
I'm me akọ me adum na election.
Down. Akono amata omo case ebi okun dai na o ranting time na nta na intru akono so that dey be sign through ho awende Asimu. Eno ma yesi misi oyi na mkowe. Eno me nkora pa. Ah. Obu ha ba fi baba krono na wa nya sika obukun. Enda mun samani yo mudo. Yo, na se omo mutin.
I cannot hear.
But from the network,
So please, does it mean that next week all of us will be going to our various centers for practicals? Next week, God willing.
That's some flexibility.
Hello.
Hello.
I'm asking that are we all going to have practicals next week on our various centers?
Yes,
As
please.
he
That's what he
said.
said. That's what he said.
So I want to find out, like this lab code, is it something that they are selling it, or you have to go and sew it?
So I think if you go to the market, you can be lucky you get some.
But
You
it's
can
not.
be
It's not
lucky
that
you get
common.
some. It's
It's not that
not that
common.
common though. It depends on where you are, say. It's not that common though. There's no dispute about that. But you can try. If you do not get some, I think he said that it will not be compulsory. So now that it has become too immediate to us, we can, if you are not able to get, say, if you are not able to get one, maybe the subsequent ones you try. You try as much as possible to get one.
Okay. So can you go to the chemistry lab without the lab coat?
So I think you are supposed to go with the lab code. However, if you do not get some, I think that shouldn't stop you from going. You
Oh,
do your
okay.
possible best within this week to get some, but if you don't get some too, that shouldn't stop you. I don't know if you have your own long sleeves overall there, if you can put it on in white shirt. Anyway, do it in such a way that your own mate will not laugh at you. But that
Mm,
one
but
it shouldn't stop you from attending. Else, Charlie, at the end, I won't mind that the one sounds one cockroach and saying, "No, I'm here."
And also basic.
okay, okay, all right. So, but the goggles, if you have a specs, you can just use that one.
Is it a go-go? If it's a go-go, they are say. If it's not a go-go.
If you don't have the goggles, you
No,
can use specs.
the gogo is more protective than the spectacles. So.
So if it's not a go-go, please go and look for a go-go. As well, like I was saying, is there anyone who can devote him or herself to teach this thing for us, so that we can be having peer teaching in our own favorable time? Is there anyone? Is there anyone? Is there
Mr.
anyone?
Mr. Festus, are you part of biology, chemistry, or you
Yeah.
are
I'm
physics,
part of
chemistry?
biology, chemistry,
Um,
biology, chemistry.
but okay, so that lady, like we last joined one. I hope it was a chemistry major.
Which lady?
Curfew.
Kafu is for chemistry major UCC Center. She is the course rep for biology major. Sorry, she is the course rep for biology major UCC Center. But in all, listen. Kafu is a course rep for all centers that is doing biology major. Are you getting what I'm saying?
Yeah, it's
She's the
like
course. Let me say,
This chemistry, she was not there. Oh,
no, she is UCC Center based.
they go to face to
UCC
face.
Center. So for them, UCC West School, I think today they went for face to face. Then the other centers, Sunyane, I don't know that of Kaswa, but I'm very sure that Kaswa also had face to face. Kaswa, Ganas, and the other center, they also had this online. This online. See, Isha. Eddie, hey, Eddie. It's not easy. It's not easy.
Okay, all right.
All right, you see what to do.
Please, so have you ended lectures for today?
Não,